Hi, this is today. I will talk about the theory of rings in this today in second lecture. Theory of rings. Okay. So remember, what's a group? Abelian group. Let me recall abelian group. Let's say A with a operation. Let's denote by addition like that. Is an abelian group. Abelian group if two things are satisfied, for five things, sorry. So that this first thing is that this addition should be a binary operation, namely it should be a function from A cross A to A. Second, it should be associative. So A plus B plus C should be A plus B plus C. So in group theory, we denoted this operation by dot. Okay, since it's an abelian group, we will denote by addition. And for every A in A, there is an element, let's call minus A in A, such that, oops, so before, so oops, not like that. So there is an element, let's call the 0 in A, such that A plus 0 is 0 plus A, that's equal to A, for all A in the group A and in A, and also for every, so this is A is the identity, 0 is the identity of A. And one more thing, two more things, that for every A in A, there is another element, let's call it minus A in A, such that A plus minus A is 0, the identity element. And also A plus B should be equal to B plus A for all A in A. So if these five conditions are satisfied, then we say that A is an abelian group. So for example, integers with addition or real numbers with addition or non-zero real numbers with multiplication or positive real numbers with multiplication, they are all groups or abelian groups, or complex numbers, for example, complex numbers with the addition again, they are all abelian groups. So that's the reminder. Next, now I will define the ring. What's the ring? So a ring is a mathematical system, formally, or let's say is a set with two binary operations first, let's denote it by plus addition, which is that's a ring R. Let's say like that. It should be a function from R cross R to R. Oops, not real numbers. To the set R, and also multiplication we will denote by dot. Also, it will be binary operation from real numbers to real numbers, to R to R, sorry, not real numbers. So a ring is a set with two binary operations like this, such that such that the first thing is that this R with this addition should be an abelian group. Abelian group. And second, this multiplication is associative. So A dot B dot C is should be equal to A dot B dot C. So this is associativity. And this multiplication should distribute onto addition. So we call this addition, although it need not be the addition and the real numbers or complex numbers. It's just the notation, this plus and multiplication. And we call this operation as multiplication. Just like in the real number case, so this R, the set R with addition must be an abelian group, and this multiplication should be associative, and also it should distribute onto addition. A plus B plus C must be is equal to A, B plus AC. It should distribute from both sides. So BA plus CA. So if these conditions are satisfied, this is for all, of course, for all A, B, C in R. If these conditions are satisfied, then we say that this R plus and this multiplication is a ring. Okay, that's a ring. So examples. So this zero identity element of identity. So this addition R with identity of this addition is denoted by zero. Just like in the real numbers, we denote by zero, and the additivity inverse, the inverse of A in, as we defined above, in our this abelian group is denoted by minus A. So since R plus R with the addition is an abelian group, every element has an inverse, and we denote this inverse by minus A. And we will write as usual that A times B for AB. So we will not write A dot B. Instead, we just write A times B, AB, like that. Okay, what else? If this addition, this multiplication need not be commutative. If it is, if this multiplication is commutative, if AB is equal to BA for all AB in R, then we say that R is a commutative ring. Commutative ring. And also, if there is an element less denoted by 1, or sometimes in order to stress the ring, let's write let's denote like this 1R. If there is an element like that in R, such that 1 times A is equal to A times 1 is equal to A for all A in R, then we say that this 1 is called is the multiplicative unit, multiplicative identity. identity of R. Okay. And if R has a, in this case, we say that R is a ring if there is one, there is a multiplicative identity. R is a ring with one, with identity, with one. So here's some examples. So most important examples to understand what's a ring. Examples. So the first one, the trivial example is sort of trivial. Addition with the multiplication is a ring. Is a ring which is commutative with identity. So it is commutative. Multiplication is commutative. And second, also, of course, the real numbers or complex numbers or rational numbers are all rings. With the usual addition and multiplication, these are rings. Commutative rings with one. One more, a non-trivial example is that let's take M2R as, namely, this is the set of all 2 by 2 matrices A, B, C, D, such that is A, B, C, D's are real number. Then there is a addition in this set. Let's call it denoted by R. In this R, we have an addition, usual matrix addition, A, B, C, D plus, let's say, X, Y, Z, T is the usual matrix addition, A plus X, B plus Y, C plus Z, D plus T. And the multiplication, A, let me write below. And the multiplication, I define like this. Oops, sorry. Is A, B, C, D, and X, Y, Z, T. If we define the multiplication like that, like this, AX plus BZ, AY plus BT, CX plus DZ, CY plus DT. This is the usual matrix multiplication. So in this case, with these additional multiplication, this R is a ring. It satisfies all these properties of rings in the definition, all the conditions. And the zero element is, zero of this element is just the 0, 0, 0. So that's the zero element. And there's also one identity, and the identity is, as you know, this identity matrix. This is the, because if you multiply this one by any matrix, that's equal to A. It does not change the matrix at all. Okay, so that R is a ring with one, and it is not commutative. For example, if you multiply 1, 0, 0, 1 with, 0, 0 with, let's say 0, 1, 0, 0, if you multiply it like that, this is, it becomes 0, 1, 0, 0. But also, if you multiply from this side, like this, if you change the order, then this multiplication is 0, 0, 0, 0. So therefore, these two are not equal. They are not equal. So therefore, this is not commutative. That is not commutative. Not commutative ring. And if we take A to be, for example, A, B, C, D, its inverse, additive inverse is, remember, minus A, minus B, minus C, minus D, so that A plus minus A is zero matrix. Is the zero matrix. Okay, that's the examples. So here are some properties of the rings. So let's see. So let me just continue with as an example. Let's show that 0 times x is x times 0 is equal to 0 for all x in R. So if you take any x in R, this multiplication by the 0 element is 0. So let's see, how do we see that? See it. Let's see, let me do one of them. 0 times x is, remember, x is, instead of x 0, I can write 0 plus 0 times x. If I use the distribution from the left-hand side, that's equal to 0 times x plus 0 times x. And now if you add the inverse of, so every element has an inverse, additive inverse, so add minus 0 times a, 0 times x to both sides. So what do we get? So 0x plus minus 0x is equal to 0x plus 0 times x formally, and minus 0x. And this, remember, this is equal to 0 because that's the multiplicative inverse of this. Sorry, not additive inverse of this 0 times x. So that this side also you can write this as 0 times x plus 0 times 0x plus 0x plus minus the inverse of 0x. This part is 0, 0x plus 0, and if you add 0 to any element, it is equal to x. So therefore 0 times x is equal to 0. Now I would like you to show that also, as I leave this as an exercise to you, show that x times 0 is equal to 0 for all x in the ring R, in any ring. Okay. Now let's see another example of ring, another important example. Let x be any. Let x be any non-empty set. Non-empty set, and let R be the set of all functions from x to, let's say, real numbers functions. So if we define addition on this for f and g in R, so if we have two functions from x to R, if we have two functions, I may define addition of these two functions. So this must be a function from x to R, so that at any point x in x, I define it as f of x plus g of x. So this is the multiplication in real numbers. In real numbers, this is the multiplication that we define. And f times g, let's define it like that. At the point x, let's say f of x times g of x. So this is the multiplication in real numbers, the multiplication of two real numbers. So with these two operations, then then this R becomes a ring. R is a ring. So a ring of functions from X to R. And the zero element is just the zero function from X to real numbers, taking everything to zero. So this zero function maps everything to zero of this real numbers. So this is the element of real numbers. And if we define, so it says this is, it's a commutative ring, f dot g x, f dot g is equal to, you can check that this is g dot x, so that g dot f of f. So therefore, it is commutative, R is commutative. And R is commutative. And if we define 1 to be from X to R, taking everything to 1. So this is the real number 1. Then this becomes multiplicative identity. So therefore, R, so the functions from X to R, or sometimes it is denoted like this. Sometimes we may denote it like that, is a commutative ring with identity, with 1. Okay, the commutative ring with 1. So this is a different example. Okay, here are some properties. So here is another example, or proposition, let's say. Let's write as proposition. Proposition says, before the proposition, let me give one more example. This was example, I had example. Okay, example. One more example. Let A be an abelian group. For example, abelian group, take integers, for example, and let n of A is the endomorphisms of A, namely homomorphisms from A to A. A is a homomorphism, namely f of A plus B is equal to f of A plus f of B for all A, B in A. So this is and with this, we define for two endomorphisms F and G, that's defined by the addition. So this is a function from A to A. We define it as like that. So this is the addition in this endomorphisms of A. At the point A, I define it like this, f of A plus g of A. And let me define multiplication, f times g from A to A as the composition, f composed. So f dot g, I define to be f composed with g. Namely, f dot g at the point A is, I define it f of g of A. Okay. So with these two operations, addition and multiplication, this endomorphisms of A, for example, take, as I said, integers, is a group, is a ring, sorry, is a ring. Usually, in general, F composed with G is not equal to G composed with F, so that usually, and i.e., so this endomorphism is in general is not commutative in general. And it has an identity. It is an identity A to A, mapping everything to itself. So that's the not commutative, but it has a ring with identity. So, and A has one. Okay. Next. Now proposition. Proposition for every. So before this proposition, let me write this a convention. Let's write A minus B for A plus the inverse of B, additive inverse of B. Let's write like that. So proposition is, it says for any any A, B, C in R, in a ring R, A, if you multiply A with minus B, that's equal to, or minus A times B, namely, this is the A times the additive inverse of B, and additive inverse of A times B, that's equal to the additive inverse of A times B. And second is that if we take the additive inverse of A and additive inverse of B, their multiplication is A times B, A times B. And finally, third one is A times B minus C is equal to A times B minus A times C. Or also from the other side, let me write like that. Also, B times BA minus CA. Okay, let me do one of them. I will leave the rest to you. So the proof of one. So A, let's look at A times minus B. If you add this to AB, what do we get? If we affect, so since using the distributive law of the addition, multiplication onto addition, we can write it like that. And minus B plus B is 0. A times 0, we know that A times B is 0. So that means this element is the inverse of, this element is the inverse of AB. So that A times minus B is the additive inverse of AB. And also minus A times B is plus, if you add like that, this is also minus A plus A times B, distributive, using distributive law. It is 0 times B, this is 0, and that's 0. So therefore, this element is the inverse of additive inverse of AB. Minus A times B is minus AB. So that 1 is proved. And 2 is, 2 follows from this one. Minus A minus B is equal to, using the first property, I can write this as minus A times minus B. And also, this is equal to minus AB, again using the first property. But the inverse of the inverse is the element itself, so that is AB. Okay, I will leave the third one to you as an exercise, 3 exercise. Okay. Okay, here is, so remember what's a subgroup? Subgroup, if you have a group, if you take a subset, if with the subset, this subset is a, if the subset, non-empty subset, is a group with this, with the operation of the big, the group, then it's called a subgroup. For the ring, it is the same. We have the same definition. So let R be a ring. Let R be a ring. R be a ring, and S is a subset of R, which is non-empty. If S with the operations, addition and multiplication in R is itself a ring, then S is called a subring. Subring of R. This is called the subring of R. So most trivial example is that, for example, Z with addition and multiplication is a subring of. It is a subset of rational numbers or real numbers or complex numbers. So Z is a subset of, or in general, integers is a subset of the rational numbers, subring of rational numbers. Rational numbers is a subring of real numbers, and real numbers is a subring of complex numbers. So not only subset, but the subrings. And here is a proposition. So let R be a ring. And S be a non-empty subset of R. Non-empty subset of R. Then S is a subring. Subring of R if and only if X minus Y is in S and X times Y is in S for all X, Y is in S. So if this is satisfied, then it is a subgroup. And here's a proof of this statement. The proof is that this way is clear, and that way, so X minus Y is in S implies that this S with the addition is a subgroup of, remember from this group theory, subgroup of R with the addition, and X, if X times Y is in S, for every X, Y is in S, so that means this multiplication is a binary operation on S. So therefore, it follows that, and the other properties of the ring comes from the properties of addition and multiplication in the real numbers. So it follows that S with this addition and the multiplication is subring of R. Okay, I will finish this lecture here and continue with the. I will continue with the with this ring theory in the next lecture.